So welcome you to today's lecture. Can you see the screen?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
great. So today what I'm going to do is I'll give a brief introduction of statistical inference problems. So I'll explain what you mean by statistical inference and what are the basic elements of the statistical inference problems. So first, let us try to see what are the statistical inference problems. So let's look at what are the statistical inference problems. Now, a basic situation in any statistical inference problem is that we have a population which is normally very big in size, and we seek information about some numerical characteristics of this population. Now, for reasons beyond our control, now that could be due to the cost, time, or even the size of the population. It may not be possible, or it may be just totally impractical to examine the entire population. It may be too time consuming, or it may be too costly, or sometimes it may be totally even impractical to examine the whole population. However, it may be possible that we can examine just a part of a population, which we call as a sample. So what we have is whatever information I have about the population, that is in form of a sample, which is just a part of the population. Let me define what you mean by a parameter. Any unknown numerical characteristic of the population under study is called a parameter. So any numerical characteristic of the population, that is called a parameter. Now the basic goal is to draw conclusions or inferences about the unknown parameters of the population on the basis of the limited information contained in the selected sample. Note that I cannot examine the whole population. What I have at my disposal is just a sample, a part of a population. Just based on the information contained in the sample, I want to gain information about the unknown parameters of the population. Now note that the sample only contains partial information about the population because it is just a part of a population. So it does not contain all the information which is there in the population. Based on this limited information, I want to make conclusions or inferences about the unknown parameters of the population. An example, let us look at heights of all Indian male students. So here your population is basically all Indian male students. The numerical characteristic in which you are interested is the heights of the units in the population. Let us consider the following two goals. I consider the goal number one, where I'm interested in estimating the mean height of Indian male students. So what is the mean height of all Indian male students? That is the goal number one. The second goal which we consider is that somebody makes a claim that the mean height of Indian male students is less than 5 feet 4 inches. And I want to test this claim. So these are two different goals which suppose I am encountered with. Now, as I said before, for the above two goals, the parameter of interest is the population mean, because I want to make inferences about the mean height. So the parameter of interest is the mean height, which I'm calling as theta, which I do not know. Now, under goal one, which is to estimate this theta, or to estimate the mean height of Indian adults, we want a point estimate depending on the sample observations for theta. And under goal two, we are keen to test the hypothesis that theta is less than or equal to 5.4, because that is the claim which is being made by someone. So I want to test those claims, and the only information I have at my disposal is the sample. I do not have information about the whole population. I have only information which is contained in my sample, which only has partial information about the population. So it is impractical to measure height of each and every Indian male student or Indian male adult, because that may not be possible, although that would be the best thing to do if possible. Because if you can measure the height of each and every Indian male adult, then you can answer these two questions in an obvious manner. You can calculate the mean and see whether what that value is. You can take that as an estimate. And if that value is less than or equal to 5.4, you can agree with the claim made that the mean height is less than or equal to 5.4. But measuring height of each and every Indian male is impractical. So what you do is so it is impractical to measure height of each and every Indian male adult to achieve goals 1 and 2. So we draw a sample of Indian male students and measure their heights. So I take an appropriate sample of Indian male students. Based on the information contained in the selected sample, that is the height of male adult in the selected sample, we try to answer the questions raised under the above two goals. So I have a partial information about the population, and whatever partial information I have, based on that, I want to make inferences about the population mean. Now, how to choose the sample? That is very important, because larger the sample size, more information you have. If larger sample size is infinite, that means you can examine whole population. You have all the information. So normally the sample size would be decided based on the resources which are available to you. We would like that the selected sample is a true, trustworthy representative of the target population. For example, in this example of heights, if one gives you a only sample of males from Haryana state, that is a very biased sample. Why? Because it's a well-known fact that males of Haryana state are generally taller in height in comparison to males in the other state. So such a sample will not be a true representative of the population. If your all sampling units are from the Haryana state, that is not a true sample. So you would like that your sample is a true representative of the target population. Now, so a big question is how to draw a representative sample. Now, there are various sampling schemes through which you can draw a representative sample depending on the circumstances at your hand. And there is a separate course on sampling theory, which you might have already done. And in this course, you learn about the various ways in which you can draw a representative sample. The most common one is the simple random sample. And then you have a stratified random samples, systematic random samples. Each of these sampling schemes have advantages over the other in specific situations. You cannot say that in all the situations one is uniformly better than the other. But the most commonly used sample is the simple random sample. Now, irrespective of which sampling scheme you choose, the bottom line is that the samples should be selected without bias, and that it is a true representative of a target population. So your sample should be selected without bias, and it should be a true representative of the target population. For example, in the case of sampling every unit from the Haryana state, that is a biased sample, because you are only choosing units from the states where males have a tendency to be taller. So now let us describe the model which we are going to study. Now note that a typical individual in the population has a height. Now this height keeps on varying. Now if you have selected a sample or selected an individual at random, it would be a random height. So suppose X is such a random variable which represents this random height. So suppose X is a random variable or a random vector for that matter of fact, that describes the numerical characteristic of the target population that is of interest. For example, in the case of height, X could be height of an Indian male selected at random from the population of Indian adult males. Now, every random variable has a distribution function, so I assume that F is a distribution function, which basically talks about, so if I look at F of X, which is probability X less than or equal to X. Because all the information about X is contained in its distribution function or the probability mass function or probability density function. Now, in the discrete case, you know that Fx is probability X equal to X. Now, in the continuous case, this is limit H going to 0, probability that X lies between X to X plus H divided by H, which is basically limit H going to 0 of F of X plus H minus F of X divided by H. This is in the continuous case. So what a statistician do is, a statistician can observe an observation, say x1, x2, xn on random variable x. So x is a height of a typical Indian male adult. So what a statistician can do is, it can choose n individuals and it can measure their heights, which are x1, x2, xn. Now each xi can be regarded as the value assumed by some random variable xi, because this xi is the height of the individual, ith individual in the sample. Now ith individual in the sample could be any of the individual from the population. So it is a random variable. So the xi which you observe can be regarded as the value assumed by a random variable xi. Now this xi would have a same distribution as x. Why? Because it is coming from the same population. So xi would have a same distribution as x. So when I say that is equal to d, means they are equal in distribution. So what you have at your disposal is x1, x2, xn, which is a sample of size n taken from the population. Now, as I explained just now, these x1, x2, xn can be considered as copies of random variable x. X is a typical numerical characteristic of a population. X1, x2, xn is the n values of x which you observe in terms of a sample taken from that population, a sample of size n. Now, each of these x1, x2, xn have a distribution function f and probability mass function of PD of f. If I look at small x1, x2, xn, these are nothing but realizations or observed values of the sample. I consider G of x1, x2 as joint PDF of these random variable x1, x2, xn, which is the joint PDF of the sample. Capital G, I consider as a joint distribution function of my sample x1, x2, xn. So a type of samples that have intuitive appeal are called random samples. So mostly we deal with the random samples. Throughout this course, we'll be dealing with random samples. And what do you mean by random samples? You might have done it in the sampling theory, that each of them have a same chance of getting selected in the sample, and they are drawn independently. So your sampling is with replacement. So the sample x1, x2, xn is said to be a random sample if x1, x2, xn are independent and identically distributed. Now, if that is the case, then you know that G of x1, x2, xn, which is a joint PDF or PMF of your whole sample x is x1, x2, xn, because they are independent. So it will be the product of individual probability mass functions and distribution functions, but each of them have a same PMF because they are coming from the same population. So each of them would have a PMF. So PMF at the point xi. Now, in general, any collection of IID random variables is called a random sample. So what is your random sample? Random sample is basically any collection of IID. IID means independent and identically distributed random variables. Now note that in practice, we may not always have random samples. So depending on the sampling scheme, we may have a sample that may not be a random. You see, all of them would have a same distribution. Each x1, x2, xn would have a same distribution because they are coming from the same population. So this condition would always be satisfied, that each xi has the same distribution as x, I is equal to 1 to n. So the only way in which your sample may not be random sample is due to the fact that they may not be independent. And that is what is being said over here, that depending on the sampling scheme, we may have a sample that may not be random. That is, x1, x2, xn may not be independent, because identically distributed will always be satisfied because they all are coming from the same population. So one situation where x1, x2, xn may not be independent is, for example, when you're doing sampling without replacement. You know, in sampling without replacement, the unit drawn on the second occasion depends on what unit was drawn on the first occasion. That means if x1 represents the value of the numerical characteristic drawn in the first sample, and x2 is the value of the numerical characteristic drawn on the second sample, then certainly x2 is going to depend on x1 if your sampling is without replacement. So the purpose of this paragraph was to emphasize that in certain situations you may have non-random samples also. But you know that if your sampling is without replacement and your sample size is large, then these xi's are approximately independent. So for large sample sizes, there would be again a random sample, even if the sampling is without replacement. But in general, when you are doing sampling without replacement, the sample you get may not be a random sample. Please feel free to ask any questions if any doubt arises in your mind. Anywhere, any one of you can ask a question anytime. Now, sometimes what may happen is your sample contains all the information that you have. But sometimes all the information about the unknown parameter that is contained in the whole sample x1, x2, xn may be squeezed into a function of x1, x2. That means it is squeezed. That means you have summarized information x1, x2, xn in some other form. To see an example of that, for example, if the parameter of interest is the population mean, then rather than considering the whole sample x1, x2, xn, one may concentrate only on the sample mean. So in that case, if your parameter of interest is the population mean, it may be desirable not to look at the whole sample, rather just look at the sample mean, which is calculated from x1, x2, xn. So that means all other information other than the sample mean is a redundant information in that situation. Now this leads to the definition of a sample statistic. What is a sample statistic? Any function t of x1, x2, xn of observable sample x1, x2, xn that does not depend on any unknown parameters of the population is called a sample statistic, or simply a statistic. Note that since t does not contain any parameter, a sample statistic does not contain any parameter. It only depends on the quantities x1, x2, xn, which are random variables. So it is a function of a random variables. And you know that any function of a random variable is again a random variable. So note that any statistic is a random variable whose probability distribution depends on the joint distribution of observables x1, x2, xn. Because t is a function of x1, x2, xn. So its distribution is going to depend on what is the joint distribution of x1, x2, xn. Now let's consider examples of some common statistics. So let x1, x2, xn be a random sample from a population with PD of f. So most of the time, as I said in this course, I'll be dealing with a random sample, which basically means that x1, x2, xn are IID. So the first sample statistic is the RS sample movement, which we define by MR prime, which is the average of xi to power r's. R can be 1, 2, 3, so on. So this is how we define the sample movement. Then we define sample mean, which is nothing but the first sample movement. So this is the first sample movement. Then I can talk about RS central movement, about the sample mean x bar n, which I defined as 1 upon n, summation I is equal to 1 to n, xi minus x bar n to power r. R can be any integer, 1, 2, 3, and so on. I can define the sample variance, which is nothing but the second sample central movement. So sample variance, which I denote by Sn square, which is m2 1 upon n summation xi minus x bar n whole square. Nothing but second sample movement. Then there's a notion of standard deviation, which is the square root of variance, the positive square root of variance. So Sn, which is square root of Sn square, is called the sample standard deviation. Now you may notice that in certain books, a sample variance is defined with a multiplier 1 upon n minus 1, not 1 upon n. And there is a reason for that, because you know that I have to make an unbiased estimator of population variance, then I need a multiplier as 1 upon n minus 1, not 1 by n. So sometimes Sn minus 1 square, which is 1 upon n minus 1, summation xi minus x bar 1 whole square, that would be called the sample variance. And Sn minus 1, which is basically square root of Sn minus 1 square, will be called the sample standard deviation. Then you have order statistics. I define x round bracket r as rth smallest of exponential x. So that x1 is the first smallest, so that means smallest one. x2 second smallest, so which would be bigger than x1. So probably x1 less than or equal to x2 less than or equal to xn would be n. Now this xr is called the rth order statistic. So rth smallest of exponential to xn is called the rth order statistic. And this whole collection x1, x2, xn is called order statistics corresponding to sample x1. So these statistics are also of importance in various situations. Then there is a notion of a sample median, which is median of x1, x2, xn. You know that this is the middlemost observation. So if we arrange x1, x2, xn in increasing order, your middle would be x of n plus 1 by 2. If n is odd, then you can get the unique middle one. That is a sample median. Now, if n is even, there may be two middle observations, n by xn by 2 and xn by 2 plus 1. Now, note that when n is odd, n plus 1 is even. So n plus 1 by 2 is a natural number. So this order statistics makes sense. But when n is even, n by 2 will not be an integer. Sorry, n by 2 would be an integer, but n plus 1 by 2 will not be an integer. So here you'll get a two middlemost observations, xn by 2 and xn by 2 plus 1. For example, let's look at what happens when n is equal to 4. When n is equal to 4, you have x1, x2, x3, and x4. So the middlemost observations are 2, x2 and x3. I take their average as the sample median. Now note that when n is equal to 5 was there is a unique middlemost observation, x1, x2, x3, x4, and your median is middlemost is only one x3, 2 on this side, 2 on that side. So this is the median. However, when n was 4, I could see that there is no middle one. There are two middle ones, x2 and x3. On left of x2, 1, on left of, so median is somewhere in between, which is the average of this x2. Then there is another important statistic, which is called the empirical distribution function, which is defined as fnx, which is 1 upon n, summation I is equal to 1 to n, indicator that xi less than or equal to x. Where what does indicator xi less than or equal to x means? This takes value 1 if xi is less than or equal to x and 0 greater than x. All right. So what is happening is you look at each xi, if that xi is less than or equal to x, this indicator function counts 1. So this is also called a counter. And if xi is bigger than x, it doesn't count. If I look at this whole sum, it is nothing but sum of observations, some of the sample elements which are less than or equal to x. That means how many elements are which are less than or equal to x. If I divide it by the total number of elements, it becomes proportion of elements x1, x2, xn that are less than or equal to x. Now, you know that your xi's are arranged in increasing order. So x1 is the first one, x2 is the second one, x3 is the second last one. So let's look at what is the proportion of observations x1, x2, xn that are less than or equal to x. Now note that if x was less than x1, x was strictly less than x1, then there is no sample observations which is less than or equal to x1, because x1 is the smallest one. If x is less than x1, is a 0 observation. If x is bigger than or equal to x1 and less than x2, so that means x is over here, then the observations less than or equal to x is only 1, which is x, is 1 by n. Similarly, if x was over here, then the number of observations less than or equal to this quantity would be x1 and x2. So 2 observations, and proportion would be 2 by n. And similarly, if x was between xi to xi plus 1, number of observations less than xi would be I, xi minus 1, and x2. So proportion would be I by n. And similarly, if x was between xn minus 1 to xn, except xn, all the elements would be less than or equal to x, because xn minus 1 is less than or equal to x. So xn minus 2 would also be less than or equal to x. X1 would also be less than or equal to x. The proportion would be n minus 1 by n. However, if x was bigger than or equal to xn itself, so that means your x was over here, then observations which are less than or equal to x is all the observations x's, because their order statistics are this. So all observations would be less than or equal to x if x is bigger than or equal to x. Okay? So this becomes 1. Now this is the empirical distribution function. Now one can check that empirical distribution function is a proper distribution function. In fact, it is a proper distribution function, but discrete distribution function. To check it is a distribution function, what I have to check? F of minus infinity is 0. X less than x1 is 0, so f of minus infinity is 0. F plus 1 should be 1, because for x greater than or equal to xn, it is always 1, so f of plus infinity is 1. It should be non-decreasing, so you can see it is non-decreasing. For x up to x1, it takes only value 0. If x increases in the interval x1 to x2, the value increases from 0 to 1 by n. If x goes further right, and it further increases to interval x2 to x3, the value becomes 2 by n. So here, the value is 0, so you can check. So if I take n is equal to 4, for example, if x1, so I have x1 over here, x2 over here, x3 over here, and x4 over here. For x less than x1, this is 0. So this is 4 value. X between x1 to 1, it is 1 by 4. We can see now there is a jump from 0 to 1 by 4. Then it would be 2 by 4. For x between x2 to x3, it is 2 by 4. So then x equal to x3 to x4, it would be 3 by 4. It would be, let me just see. X3 to x4, it would be 3 by 4. So this is 3 by 4. And then x greater than or equal to x4. So you can see it is non-decreasing. It is a step function. And it is right continuities through the construction, because left-hand limit at x1 is 0. Value of the function at, so within these intervals, it is continuous. So the only point of discontinuities could be these order statistics, x1 or x2 or x3 or x4 or so on. So look at x1. At x1, the value is 1 by n. What is the right-hand limit? Right-hand limit is also 1 by n, because in this interval, we'll approach x1 only through right, 1 by n. So it is right continuous. So it is a proper distribution function. Now let's talk about the sampling distributions. Now the distribution of a sample statistic is called a sampling distribution. So what is a sampling distribution? It is a distribution of any sample statistic. So let's look at some of the important sampling distributions. One is the normal. I have given you PDF over here. You know its mean, the mu, its variance is sigma square, its movement generating function, you know. So these are very well studied normal distribution. I would ask you to just remember its functional form. its mean, its variance, and movement generating function. Another important distribution is gamma distribution, which is related to a gamma function. You know that gamma function is a function defined on 0 to infinity. It is a real valued function. And how do you define gamma? Gamma of alpha for any positive real alpha is defined to be integral 0 to infinity e to the power minus t to the power alpha minus 1 dt. Now, a natural question as a mathematician or a statistician, which one should ask is, what is a guarantee that this integral is a convergent integral? Does this converge? I leave this to you. It's a basic calculus problem. One can show that this is convergent. The answer is this integral is convergent if alpha is greater than 0. In fact, for alpha less than I equal to 0, this integral is divergent. So that means this definition makes sense, because since this integral is convergent, it will have a fixed value. I define that as a gamma alpha. The function gamma alpha is called the gamma function. Now one can immediately see through integration by parts that gamma of alpha plus 1 is same as alpha times gamma alpha. How do you do it? You take this as a differentiating factor, e to the power minus t as an integrating factor. Then you can reduce this integral, because integral of e to the power minus t is minus e to the power minus t. Now, if you use that, you can reduce this integral in terms of alpha minus 1 t to the power alpha minus 2. And e to the power minus t would remain e to the power minus t with a minus sign when you integrate it. So gamma alpha can be related to gamma alpha minus 1. So gamma alpha. So gamma alpha plus 1 is related to alpha gamma alpha. So that is how you do. One can easily prove that gamma of half is same as root pi. In fact, gamma of half is nothing but 0 to infinity e to the power minus t to the power minus half dt. So that this is same as root pi. I can give this exercise. This is a standard exercise. You can easily prove it. Now, one thing to note is, if this alpha was integer, then gamma of n would be n times gamma of n. But gamma of n would be n minus 1 times gamma of n minus 1. So if you keep on doing that, what you observe is gamma n is gamma n minus 1, factorial of n minus 1, because you can keep on doing it, and finally the thing which you get is gamma 1. And what is a gamma 1? Gamma 1 by definition is nothing but 0 to infinity e to the power minus t to the power 1 minus 1, which is t to the power 0, which is 1, so e to the power minus t dt, which is 1. So gamma of n, for example, if you have to see gamma of n by part 1, would be nothing but n minus 1, 1 less, times gamma of n minus 1. N minus 1, now again apply gamma of n minus 1, I again use this formula. It would be gamma of n minus 2 of n minus 2. So keep on doing this. This will become n minus 1, n minus 2. Go up to 3, 2, and you will get 1 times gamma of 1. But gamma 1 is 1. So this is 1. So it becomes 1, 2, 3, n minus 1, which equals to 2. So gamma n is same as factorial n minus 1. And you have already seen what is a gamma distribution. Gamma distribution is a distribution whose support is 0 to infinity. That means it takes only positive values. And its PDF is given by 1 upon gamma alpha, theta to the power alpha, e to the power minus y theta, y to the power. So it has two parameters, alpha, which is called a shape parameter. Why it is called shape parameter? Because as you vary alpha, your PDF of gamma has a different shape. So alpha determines the shapes. Theta is the scale parameter. Similarly, normal distribution has two parameters. One is the mean and one is the variance. So normal distribution has mu, which is the mean, and sigma square or sigma. So in that sense, gamma distribution is a family of distributions. Why is a family of distributions? Because as you change mu and sigma square, you get a different normal distribution. So I have a family of normal distributions, normal mu sigma square, where mu can be anything from minus infinity to infinity, and sigma can be anything from greater than 0. So normal is a family of a distribution. In the same way, since for different shape parameter alpha and different scale parameter theta, you get a different gamma distribution, this is also a family of distributions. Gamma is also a family of distributions. Now you know that its mean is alpha theta, variance is alpha theta square, its moment generating function is 1 minus theta t. Now some particular cases of gamma distributions are of interest. One such distribution is the exponential distribution. So I say that a random variable x has exponential distribution, which I write down as x has exponential theta, if x is gamma theta 1. So exponential distribution is a special case of a gamma distribution with alpha as 1. You can see if alpha I put it as 1 in gamma distribution, I get y to power 0. So you get density only as 1 minus y theta. And gamma of 1 is 1. So you get a theta power alpha becomes 1 by theta. So the density is 1 by theta e to power minus theta. So its mean is theta, variance is theta square, moment generating function is 1 minus theta t to power minus 1. Now let's consider another particular case of chi-square gamma distribution, which is a chi-square distribution. I would say that a random variable x has a chi-square distribution with new degrees of freedom, and nu is a positive integer. For any positive integer nu, I would say a random variable x has a chi-square distribution with new degrees of freedom, which I write down as x has chi-square nu. If the distribution of x is gamma 2 nu by 2. So if you, in the PDF of gamma distribution, if you put alpha as n by 2 and theta as 2, you get chi-square distribution. So its PDF would become 1 by 2 to power nu by 2. Gamma nu by 2, e to power minus y by 2, y to power nu by 2 minus 1 for y positive, 0 otherwise. Its mean and variance, you know, its moment generating function is 1 minus 2 t to power minus nu by 2. Another distribution which is of interest is the student t distribution. For any positive integer nu, a random variable x is said to follow a t distribution with new degrees of freedom, which we write as x follows t nu, where nu is any positive integer. If its PDF is given by gy, which is gamma of nu plus 1 by 2, gamma nu by 2, 1 upon root nu pi, 1 plus y square by nu, 2 power nu plus 1 by 2. And y can take any value from infinity. One can check that this is a proper PDF. So one can check that this quantity, if integrated out from minus infinity to infinity, gy dy will all. Now, the mean would exist if nu is greater than 1, and mean would be 0, because this distribution is symmetric. So if nu is greater than 1, that means degrees of freedom are greater than 1, the mean would exist and it is 0. Similarly, the second moment or the variance would exist if the degrees of freedom are greater than 2. And in this case, variance would be nu upon nu minus 2. Now one can see that T1 distribution has a density gamma of 1 plus 1 by 2, which is gamma of 1, which is 1. Then gamma of 1 by 2, which is 1 by, gamma of 1 by 2 is root pi. So it is root pi. New one, so root pi becomes 1 by pi. 1 upon 1 plus y squared to power 1 plus 1 by 2. So it is 1 plus y squared only. So T1 distribution is nothing but a Cauchy distribution with PDF 1 by pi 1 plus y squared. And you know that for the Cauchy distribution, mean does not exist. And reason is because nu is equal to 1 is smaller than 1. So for the Cauchy distribution, the mean does not exist. Another sampling distribution which is of importance is the Snetker's F distribution. For positive integers nu1 and nu2, a random variable x is said to have an F distribution with nu1 and nu2 degrees of freedom, which we write as x has a distribution f of nu1, nu2, if its PDF is given by 1 upon beta of nu1 by 2, nu2 by 2, nu1 by nu2 to power nu1 by 2, y to power nu1 by 2 minus 1, 1 plus nu1 by nu2, y to power nu1 plus nu2 by 2, for y greater than t. F distribution takes only positive values, T distribution takes any value from minus infinity to infinity. Now one can check that minus infinity to infinity, Ty, which would be basically 0 to infinity Ty. Now, where B, AB is the usual beta function, one can check that the mean of our F distribution is nu2 upon nu2 minus 2, the second degree of freedom, provided nu2 is greater than 2. For nu2 is equal to 1, the mean does not exist. Variance of x is 2 nu2 squared, nu1 plus nu2 minus 2, nu1, nu2 minus nu1 squared, nu2 minus 4. And the variance would exist only if the second degrees of freedom is greater than 1. Now, I can talk about some results on sampling distributions. So let x bar n and Sn squared, which I'm taking as here as 1 upon n minus 1, summation xi minus x bar whole square, with the sample mean and the sample variance respectively based on a random sample x next to xn of population having PMF, PLPFF. Let mu and sigma square and mu4 respectively be the mean, variance, and the fourth central moment of F. So what is mu? Mu is expected value of x1. Sigma square is variance of x1, which is expected value of x1 minus mu square. What is mu4? Mu4 is expected value of x1 minus mu whole 4. Now, if that is the case, then you know that if you have a random sample, then expected value of x bar n would be mu. Variance of x bar n would be sigma square by n. Expected value of Sn square, note that here I have a 1 upon n minus 1. So to get expected value of Sn square is equal to sigma square, I need to have a multiplier 1 upon n minus 1, provided sigma square is less than infinity. One can also find out variance of Sn square. That will turn out to be in terms of a fourth central moment, 1 upon n mu4 minus n minus 3 upon n minus 1 6 or 4, provided mu4 is less than infinity. No one can easily prove this. You might have already seen the proofs of this in your bachelor's level or even in one of your earlier courses. So I would say that you review this and try to derive it of your own. The proof is straightforward. Now I see I'm coming to an end. Let me just do this small theorem which you know about normal distribution. That if x has a normal distribution with mean as mu and variance as sigma square, then x minus mu by sigma would have a normal 0, 1. It's a standard result which you do at your bachelor's level. Not only that, you know that square of any normal 0, 1 is chi-square on 1. So z square, which is x minus mu whole square by sigma square, would have a chi-square on 1 degrees of freedom. These are well-known fact. So this is all where I would like to stop today. So let me just mark it over here, end of lecture on today is 6 January 20. Let me stop over here. We'll meet tomorrow since we don't have any homework so far. So tomorrow we'll meet, but it would be a lecture. So I would continue from wherever I'm leaving today, and I'll try to finish rest of the module 1, and then I'll try to get into module 2 as well. Now, if anybody has any questions, you may ask it now. And those who do not have a questions or do not want to participate in whatever questions are being asked by anyone, they may leave. If you have any questions, feel free to ask. Any questions? Okay, so if there are no questions, I would assume that we can leave. I would wait for you to leave, and I would be the last one to leave in case somebody decides to ask a question. So you may leave if you want, you may leave the meeting. If anybody wants to ask a question, he can stay back, others may leave. So I still see that 2 more persons are over here. If you want to ask any questions, the remaining 2, Arun Renga and Pratik Soni. Can you hear me? Arun, can you hear me? Pratik, can you hear me? Arun, can you hear me? Okay, so let me just end the meeting over here.